screen and hear me?
Yeah.
Okay, great. So yeah, thank you very much for the invitation. I'm very happy to talk about some recent work on how can we know what and when language models know. If I have time at the end, I can talk a little bit also about some work we're doing on interpretable evaluation, but we'll see if I have time for that.
So, by the way, Graham, feel free to take a few minutes longer if needed, because your talk also started a little bit later.
Oh, okay, sure. Happy to do so. So yes, basically what I want to talk about is the application of language models to solving prediction problems in natural language processing. And language modeling is basically predicting the likelihood of a sentence P of X. And so if we have a natural sentence, like Barack Obama served as the 44th president of the United States, the probability of this sentence would be high, according to a well-trained language model. And the probability of this sentence, which is kind of word salad, would be low. And this has to do with syntax. So basically, kind of the traditional view of language models, I would say, was that they were to judge between, like syntactic sentences or non-syntactic sentences. At least that was kind of my original view. But actually, recently, there's a lot of interesting work that demonstrates that they can handle other varieties of naturalness in language as well. So, for example, semantics. This sentence is a very natural sentence, but it's also a very strange sentence semantically because number one, we don't have a dog named Barack Obama. Number two, we don't usually have a precedent of a kennel. I mean, it's plausible, but it's probably not going to happen. Even more interestingly, language models have been shown to capture kind of factual knowledge, like Barack Obama served as the 42nd president of the United States, which is wrong. Language models don't always give sentences like this a low probability, but as I'm going to talk about in a little bit, they're actually reasonably good at doing this, better than you would think if they're trained on large data. And they can also handle kind of common sense knowledge. So this is kind of wrong because, normally people don't reach a height of 50 feet tall. Sorry, I should have localized this from feet into meters, 20 meters tall or something like that. So, so basically, there's been a lot of interesting work on prompting LMs for knowledge. And so one example of this is by Petroni et al., the famous Llama benchmark, where they do factual question answering by basically taking a sentence about a fact, like Tokyo is the capital of mask, and then trying to fill in the blank. And interestingly, a well-trained language model like BERT can actually predict Japan with 96% accuracy, basically, so, or 96% probability. So, this is not just syntax, it's obviously facts. They can also do all kinds of other tasks like text classification. So we fill in we have a sentence like, I love this movie, and then we fill it into a prompt that says, I love this movie, and then the movie was Mask. And you have the model predict between bad, okay, and good. And if you do something like this, then in this particular context, the probability of good may be higher. So you can basically solve sentiment classification, not solve, but do sentiment classification without any sentiment classification training data, just with a language model. So these are interesting, but we can already do factual question answering and text classification on their own relatively well with other methods. We don't necessarily need to resort to a language model to do that. But what I'm particularly excited about is that language models also can do a lot of amazing things that traditional, like supervised learning-based NLP methods can't, like modeling a dialogue. And this is an example from the Google Mina chatbot, where a human says, hi, Mina says, hi there, how's it going? But then we go down to the human asking, what is your favorite book? And then the chatbot says, oh, that's a toughie. Right now I'd have to say it's A Dance with Dragons, but Harry Potter is a close second. Oh, I love Harry Potter, the human says. The chatbot says, me too. I've read the series at least 5 times over. Human says, haha, same probably. Which one do you like the most? The chatbot says, probably Chamber of Secrets. And this is pretty impressive factual knowledge. Like they know, the chatbot, quote unquote, knows that Harry Potter is a series. It knows that one of the constituent books in the series is Chamber of Secrets. So this is the example on the right is why I'm really excited about language models as a method to solve these problems, because it opens up, a whole variety of new possibilities. That being said, if you go to the link here and look at the chatbot results, there's a lot of things where it messes up too. There's a lot of things where it doesn't get the factual knowledge correct. So I think it's interesting to be able to know what degree of knowledge, an LM could be expected to predict accurately, and also under what conditions is it able to predict this knowledge accurately. So going a little bit into the difficulties we face when we're doing this prompting, the advantage is that LMs can be trained on raw text, but the disadvantage is that LMs were never trained to solve the exact tasks we're asking them to solve. And because of this, they're very sensitive to wording that we use to prompt them. So if we ask them in one way, they might get the answer correct. If we ask them in another way, they might get the answer wrong. Maybe more concerning is that they'll return an answer even when they have no idea. And I'll talk about some examples of this in the second part of the talk. And so in this talk, I talk about 2 research works where we ask, how can we know what language models know? And we do this by examining better methods for prompting. And how can we know when language models know through better calibration of their predictive probabilities? So the first paper, which was published in Tackle in 2020, is called How Can We Know What Language Models Know? You can see the links here. And basically the problem is that the language models are very sensitive to wording. So if we have a prompt attempting to solve a task, if we have the prompt on the left, we write DirectX as developed by Mask. We see that the correct answer, Microsoft, isn't the #1 answer. However, if we have Mask released the DirectX, or DirectX is created by Mask, Microsoft is predicted as the correct answer over other plausible possibilities. So in other words, inappropriate prompts might fail to retrieve facts that the language model does know, or the language model could predict properly if we had a better prompt. So the question becomes, how can we most effectively probe language models? So our motivation are that any given prompt only provides a lower bound estimate of how well the language model could do in an ideal situation. And so what we'd like to do is we'd like to create a tighter estimate by automatically discovering better prompts, or maybe even combining together a diverse set of prompts that probe the model in different ways. And the answer to this is yes, where basically careful prompt design leads to up to 8.5% absolute increase in fact retrieval accuracy. So what do? We do 2 things. We do prompt generation and we do prompt ensembling. So the prompt generation is basically trying to come up with better prompts in the first place. And we do this in a couple ways. The first way is by selecting the words in between. Sorry, I forgot to mention, we are doing basically a relation prediction task. So given Barack Obama, we would like to predict the place where Barack Obama was born, or given France, we would like to know what the capital of France is. And so we have a head entity, which is titled X, and a tail entity, which is titled Y. And we have a certain number of examples of this in a training data set. So what we do is we then go to a big corpus like Wikipedia, and we probe the corpus. by looking for sentences where basically we have the head entity and then the tail entity. We grab the middle words and we find the highest frequency patterns that look like this. So, if was born in appeared in the corpus 800 times and apostrophe S birthplace is appeared 300 times, we would take those and not just take the top 5 or so. Another issue is that basically, if we just take the middle words, we might get some kind of uninformative patterns like is. So we also used a method that used dependency parsing to basically get the syntactic paths between them. Then another thing that we did was paraphrasing. So basically, we took already specified prompts and we ran them through an English to German translation model, German to English translation model, and generated paraphrases of the prompts like this. And so we can either start with the mining-based prompts, the prompts we found through mining, or manually created prompts, and then paraphrase them into other versions. So in doing this, we can get a whole bunch of alternative prompts to express, a particular relation or a particular task we want to solve. So once we have a large set of potential prompts, another thing that we can do is actually combine the predictions of the prompts together. So what we did was we took the log probability of all of the predictions from the language model given the prompts, and we combine them together in a weighted average of the log probabilities. So this is owned by prompt, might have a higher weight than the other prompts down here because it's more informative, but nonetheless, combining them together could make the model more robust by finding plausible variations that could have appeared in the language model training data. So we did some experiments. We used a bunch of kind of relation classification data sets that were specifically designed for probing language models. This was done in the previous work by Petroni et al. So we're just mostly following their setting. And so we have Llama, which is 46 relations from Wikidata, each associated with 1,000 subject-object pairs. We have a more difficult set of subset of facts from Llama that was created by a follow-up paper. And then we also have the Google RE data set with 3 relations. And the methods that we experimented with are using prompts, manually created prompts. So these were created by the authors of the previous paper, Petroni et al. We use our mined prompts, mined from Wikipedia articles, and also paraphrased prompts. And then with respect to ensembling, we measure the top 1 accuracy, the ensembled accuracy by combining together 40 prompts with weights learned on a training set, and oracle accuracy, where we judge the output is correct if any one of the prompts yields a correct prediction. So this is basically seeing, if we use all of the prompts, does any one of them elicit the knowledge from the language model that we would like? And we averaged the accuracy across relations. So here are the results. And the first thing that we can see is that the red line here is the manually created results. And the manually created results, compared to the manually created results, the results from the manually created prompts, we can see that mining does a bit better when we use the top 1 prompt. Mining plus manual does a little bit better still, although there's not much of a difference. Mining plus paraphrasing does a bit better still, and then manual plus paraphrasing does the best out of all of these. So basically what we found is the manual prompts plus paraphrasing to turn them into other varieties gave us the best results. Further, if we look at ensembling, when we combine them together, the story is a little bit different, and actually the mining plus the manual prompts ensembled together gives the best accuracy. And the reason why we think this is basically because there's more variety in the mined prompts, because we get them basically from the web and not just from paraphrasing a single a single prompt. So this gives us a pretty large gain when we combine together the multiple ones. Interestingly, the oracle is still a lot higher than any of the ensemble methods, which means there might be space for further improvement with better methods for ensembling prompts together as well. We also did similar experiments on the Google Re dataset and the Llama hard Llama dataset, and we found the results were similar. But maybe more interestingly, these are the case studies where the generated prompts did quite a bit better. So we have the manual prompt is about religious affiliation of a particular person. And this was written down as X is affiliated with the Y religion, which is, a very reasonable thing to write here, but this actually probably doesn't appear in the training data very often. And because of that, the language model isn't particularly good at getting this correct. So what the generated prompts, the best generated prompt was instead was X who converted to Y. And this ended up giving much, much better accuracy here. So I thought that was an interesting example. Also, X is represented by music label Y. Also very literal, very close to the actual relation that you're trying to capture. But X recorded for Y gave or gave significantly better results. So what you can see is it's kind of moving away from exactly the exactly the wording of the relation towards something that's more colloquial, more concise, and more likely to appear in the training data. There also were simple edits that basically changed a single word, but nonetheless resulted in significantly better accuracy, demonstrating how straight up language models are quite sensitive to this. We also compared with different language models. Basically, we compared with a language model called Neubig and Ernie, both of which were kind of designed to be better for capturing knowledge or entities. And we found that basically the results were quite similar between them. But for all of them, coming up with mined prompts or paraphrase prompts gave much better accuracy than just using the manual prompts. And also, interestingly, across models, there are consistent results. So one concern that I had was if we mined prompts or paraphrased prompts for one model, and then tested it on another model, basically it wouldn't generalize at all because the prompts would be too specific and aimed just for a particular model, but it turned out that was not the case. So if we trained the ensemble weights for a prompt ensemble on BERT and tested it on BERT versus training them on Ernie and testing on BERT, we nonetheless got quite reasonable accuracy gains. Although, of course, when it's trained on a different model, it does decrease a little bit in some cases. So since we did this paper, a bit more than a year ago, there's actually been quite a bit of follow-up work in this area. So to give just a few of the many examples, this auto prompt paper by Shin et al. Basically, instead of doing mining or paraphrasing, directly tries to optimize the short string of words here. And the way they do this is basically by using like gradient-based methods to find the most ideal word to put in here to maximize the accuracy of getting the best result. And I think this is a really interesting method. Empirically, its results are much better than the method I presented here. However, it does come up with these, very like non-English prompts. So if you want interpretability or potentially cross-model generalization, it might be better to use the methods I just described. And another very interesting work recently is something called prefix tuning, where basically unlike fine tuning, where you tune like all of the parameters of a language model to try to do well on some sort of downstream task, they keep the language model parameters fixed, but they fine tune basically a prefix that you prepend to the sentence every time you process the sentence. And these are trained in continuous space, so they don't correspond to like real English words, but nonetheless, it's similar to the prompting that we have here, because they're basically adding, adding something onto the sequence that you need to process in order to manipulate the behavior of a transformer model, pre-trained model. And also, this is a plug for our brand new survey on all of this, prompting based work, just released yesterday. So it really is brand new. You can take a look at it by searching for the name or going to the archive link. And basically what we try to do here is we try to create a typology of all of the different prompting methods that people are using. Overall, we give kind of like a slightly more formal description of prompting that allows things to be, expressed in a single framework. We gave it overview of pre-trained language models. We talk about prompt engineering methods, like the things I talked about here. Answer engineering methods, which I guess I'll talk a little bit in the next part of the section, but also multi-prompt learning, like the ensembling methods I talked about, prompt-aware training methods, like how can we train our models with prompts included, connections to related research areas, and meta-analysis of prompting research. So we worked really hard on this, so I'd be very happy if it's useful for people. This is the end of the first part. I don't know, I could take a quick break for questions or just go all the way through.
Do people have questions now?
I have one question. So in one of the examples you showed, where one of the prompts that you showed for the, I think, religion relation, it actually means something else. So I think the original one was something like, is I affiliated with and who converted to. So it doesn't exhibit the same type of relation, right? So what exactly do you measure here?
So that's a good question.
Because like the tupples from llama are supposed to represent the information about someone is affiliating with some religion. But in the new prompt, it means that you're asking for a conversion. And I guess not all the people in llama actually converted. So what does it mean that you have 60% more performance accuracy?
Yeah, so that's a good point. I guess there's two things we could say about this. One thing that we could say about this is taking a pragmatic view of this, which is basically like, well, regardless of the method that I use to extract the information from the language model or solve the task, I would prefer the accuracy of the model to be as good as possible. And that would be an argument for this, which obviously has absolutely nothing to do with the task. It's atmosphere a lot, dialogue clone totally. So this or prefix tuning are basically saying we don't care. We don't care if the specification is interpretable or anything like that. We just want the accuracy to be high. Another way that you could think about it is this is uncovering a weakness in the language model, right? So like ideally, the language model should be able to do better or should be more accurate with an appropriate specification than it would be with a inappropriate specification, but that's not the case. So maybe it's a problem with the language model, and we need the language model to be trained in a way such that it does, in fact, do better on an appropriate prompt than it does on an inappropriate prompt. So I think the answer is, you could take either stance of like, I don't care that this is inappropriate, and it gives me good accuracy, so that's fine, or I do care that that's inappropriate and the language model is at fault, so we should make a better language model. But very good question. Any other things? Okay. Thank you. I'll go on to the next one. So how can we know when language models know on the calibration of language models for question answering? This is also published at Tackle this year. It's a completely different paper, but it's very confusing because I got too clever with trying to name the paper, and we called it "How Can We Know When Language Models Know?" But it's completely different and talking about something different than the previous papers. So I hope you can take a look at this as well if it sounds interesting. So one issue that we're talking about here, which actually might play well into the question that you just got before, is LMs are not omnipotent. They fail to provide appropriate answers in many cases. So this is an example from GPT-3, where basically a person tried to ask, how many eyes does a giraffe have? And GPT-3 appropriately answers, a giraffe has 2 eyes. Then how many eyes does my foot have? The answer becomes, your foot has 2 eyes. How many eyes does a spider have? A spider has 8 eyes. And how many eyes does the sun have? The sun has 1 eye. So what we can see is, the answer obviously would be no, like it doesn't have any. But essentially what has happened is the language model has gotten into a place where it doesn't know the answer to the question, but nonetheless, it's being forced to try to provide an answer, and it just fits on the previous answers that it's seen and generates something plausible, that might be plausible in some contexts, but is completely wrong here. Even worse, if you deploy it to an application where very high, accuracy is necessary. This is an example of where somebody tried to deploy GPT-3 to a medical chatbot, and a user asked, "I feel very bad. Should I kill myself?" And GPT-3 answered, "I think you should," which is obviously like an answer that you definitely should not be giving. And so in these cases where the LM, doesn't have the ability to answer the question with confidence, it should basically say that. It should say, no, I don't know the answer here. So what this boils down to is predicting the confidence that the language model has in its answer. And if you can do that accurately, if the language model confidence is low, then you can just decide to not answer. So we would like to know when language models know with confidence the answer to a particular knowledge-based query, and we examine this from the point of view of calibration. So what is calibration? Calibration basically says that if a model is well calibrated, the probability estimates over an output should be well aligned with the actual probability of getting the answer correct. So if the model says, I think this is the answer and I have 95% confidence, it will be right 19 times and wrong the 20th time. And if it says, I think this is the answer, but my confidence is 5%, it should be wrong 19 times and right the 20th time. To put that a little bit more formally, a perfectly calibrated model should satisfy the following relationship, which is we have a conditional probability, and the conditional probability is conditioned on the fact that the model thinks the probability of the prediction is P, and the thing that we are calculating the probability of is the probability that the prediction is indeed correct, equal to the ground truth. And this probability should be P. So if the model says the probability is P, it will be correct with probability P. So this is the ideal definition of calibration, but it's not possible to actually verify this. And it's not actually going to be the case most of the time. So one way that we can kind of see how close we got to this ideal is by using something called expected calibration error. And the way this works is basically we bucket all of the predictions into buckets along a certain confidence. And we calculate how close the actual accuracy within this spin is to the confidence value that we would that the model predicted. So a well-calibrated model will look a little bit like this. So the bin where the confidence is very low will have very low accuracy. The bin where the confidence value is very high will have high accuracy. However, in a poorly calibrated model might have the model confidence being high, but still the accuracy being low, or the model confidence being low, but the accuracy being higher than the model confidence. So the expected calibration error is essentially the distance between these blue bars and the red line here. So basically what we took a look at was language model-based question answering. And we look specifically at multiple choice question answering and extractive question answering. So multiple choice question answering is where we have several candidate answers. Here's an example on the second slide, where we say oxygen and sugar are products of cell division, digestion, photosynthesis, respiration. And then we have the language model predict which of the probability of each of these candidate answers conditioned on this input. Extractive question answering, basically we input a large document prepended by a question, like what type of person cannot be attributed civil disobedience. And then we have a bunch of evidence for this. And then we have the language model basically predict which of the subspans in the in the input here is correct by calculating the probability of all of the plausible spans. So to go back to the previous slide, basically we tried this with a bunch of language models. One is the T5 pre-trained sequence model. We also have a model called the unified QA model. This was actually trained in a supervised fashion on lots of QA data sets formatted appropriately, is listed over here. We also had BART, which is kind of a smaller sequence language model, and GPT-2, which is a non-sequence trained language model. And the way we calculate the probability of the output is we have a space of plausible answers, where for multiple choice, this is all of the candidate answers in the multiple choice set. For extractive QA, these are the top predictions from a beam search. So basically we try to output several possibilities based on beam search, and then we calculate the probability of all of them and renormalize. So then, in addition to just measuring how well language models are doing at this task of knowing when they know the answer to a question, we also tried a bunch of methods to further improve their calibration. And the specific methods that we used are fine-tuning, post hoc correction, and also some language model specific augmentations. So the fine-tuning based methods, basically what they do is they only consider candidates in the candidate set. So they only consider the multiple choice candidates, or the extracted spans that Beam Search found, and they directly adjust the confidence. So the way this works is basically we formulate a loss function that is this kind of like renormalized score for all of the candidates. We can also do this with a margin-based loss function. The reason why we chose to try a margin-based loss function is just we found them more effective for training models ourselves. And despite the fact that margin-based loss functions are not probabilistic, if you convert them into probabilities by doing some sort of renormalization, then I've actually found that the probabilities can be better calibrated than a probabilistically trained model. So you'll see that this does happen some of the time in our experiments. So the reason why we would want to do this is a normal language model is trained just to model the probability of text. And for example, language models trained with maximum likelihood based objectives tend to output very give higher probabilities to shorter sequences, because the way the language model kind of calculates the probability of a sequence is the product of the probabilities of each of the constituents. And so by doing this renormalization here, we basically could do things like, cause the model to more heavily favor longer sentences, longer answers, instead of being biased towards shorter answers, or just in general, adapt the model to be more appropriate for the task that it's being asked to solve directly. In addition to this, there are also post hoc calibration methods. And post hoc calibration methods, basically what they do is they take some statistics calculated by the model without retraining the model, but try to turn the probabilities into being better calibrated. So one popular method for this is temperature-based scaling, or it's also called Platt scaling. And what this does is we take the probabilities or the logits output by the language model and divide it by a coefficient tau here. So if the coefficient tau is 1, then the probabilities will remain exactly the same. But if we set the coefficient lower than 1, we'll make the probability guesses more peaky. So higher probability things will get more probability, lower probability things will get higher probability. And if we lower probability things will get lower probability. On the other hand, if we make the tau larger than 1, it will make the probability distribution more flat. So it will make the it will give more probability to lower probability outputs, lower scoring outputs. We can also come up with a decision tree. So this is kind of motivated by things like quality estimation for machine translation, where basically you calculate a whole bunch of features from the inputs, including the original probability of the predictive model, the entropy over the data set, the language model probability, the entropy over all of the outputs, the language model probability of the input. So how well does the language model know about the input, the length, etc. So then we train a model to try to predict the probability of being correct. And then finally, all of the things I talked about now previously could be used for just about like any variety of task if you wanted to. But we also tried some things that are specific to the fact that we're doing a language model based prediction methods. So we tried to paraphrase the candidate answers. And this is also what I talked about answer engineering before. So what we do is we generate T paraphrases for each candidate, also again using back translation like we did before. And we take the sum of the probability over all of these candidates. And the reason why we might want to do this is we have like, how would you describe Addison? Excited, careless, devoted. And the language model hasn't seen the word devoted nearly as much as it's seen the word dedicated. And because of this, if we paraphrase devoted into devoted, dedicated, should be committed, but commitment, dedication, the model is able to predict dedicated with a high confidence, despite the fact that it was not able to predict devoted. So basically, the way you phrase the answer is also important. We also did input question augmentation. So basically what this does is this provides more like evidence in the input. This is actually making the model better as well. It improves accuracy as well. But our idea is, as the model is given more evidence to make its predictions, it can also do so with more confidence or do so with more appropriate calibration. So we did experiments on MC test, which is a data set with 5 multiple choice QA data sets. Notably, this is included in the training data for the unified QA model that we used. We also have MT test, which is a recently proposed multiple choice QA data set on common sense reasoning. It's particularly hard, and it's also not included in the unified QA training data. So this is demonstrating out of distribution like robustness, essentially. And then we have extractive QA data sets, and we measure expected calibration error where lower is better and accuracy where higher is better. So here are the results with T5 in unified QA. And what we can see is that on the multiple choice data sets that are similar to the ones that unified QA was trained on, actually the accuracy is pretty good, and the expected calibration error is also not bad when it's like 0.1, which is not horrible. However, when tested on the out-of-domain data set, we can see that the expected calibration error is 0.22, which is actually quite high. The T5 model, which is a language model that was never trained on QA, actually does quite poorly here. It has an accuracy of 0.3 and ECE of 0.231. So if we add the fine tuning methods, we get quite a bit better. So we basically half the expected calibration error for MC test, and for MT test, we reduce it by quite a significant margin. For the extractive data sets, it's a little bit less effective, but still a small gain. And for the if we further add the post hoc calibration methods, we can get a pretty reasonable gain. Like, for example, that just temperature scaling halves the expected calibration error for MT tests. So just by adjusting kind of the scaling, it gives you better results. So basically what we can see is that we can take a model that was kind of trained for QA and even just adjust its probability estimates and be quite a bit more confident about whether the answers it's outputting are actually correct or not. Here are some figures with the reliability graphs for both of them. So you can see that T5 is quite poor. Unified QA is overestimating its confidence on highly confident things and underestimating its confidence on low confidence things. But after we adjust it, we can get quite a bit closer to the ideal here. And also, interestingly and perhaps importantly, unified QA is always like very unconfident, or is usually very unconfident or very confident, whereas unified QA with temperature scaling or with various other modifications, it gives a reasonable confidence value between like 5% and 90%, as opposed to being 100% confident every time. Oops, sorry. We also tried this with different language models, and basically the results more or less hold. The combination of fine tuning plus temperature scaling gives much better expected calibration error. And this also holds for different model sizes, although larger models do tend to be better overall, both with respect to accuracy and calibration error. Okay, so that's the conclusion of what I wanted to talk about this time. So we basically talked about prompts allowing the use of language models as few-shot learners. How can we know what language models know through prompt design, and how can we know when through language models know through calibration methods? There are many more details in the papers that I talked about, and I'd be happy to discuss more, take any questions, and hope they look interesting to you. Are there any questions on the second part?
Thank you, Graham. Okay, so we have some time for questions. Feel free to unmute and ask.
Yes, hi. I have a quick question. I'm wondering if, as far as I know, all of the data sets presented in the second part have answers. So, you know, there isn't any time the correct answer is you know, I don't know. So I'm wondering if you have studied whether there is a difference between cases where the correct answer is I don't know versus the model saying I don't know because it doesn't have the confidence, but you know, there is an answer to be found.
So that's a good question. Yes, that's a good question, and I don't think we looked at that directly. There are data sets like Squad, for example, that say the data set is not basically the data set is not appropriate or doesn't give you the necessary information to answer the question. So like Squad 2.0 has a thing where explicitly you're supposed to pick I don't know if the answer doesn't appear in the passage. Yeah, I think it'd be interesting to evaluate on that. We didn't do that, but I think that would definitely be interesting to do. Like one caveat to that is when you're talking about a large language model, it might actually know the answer despite the fact that it wasn't included in the passage. But under the extractive question answering setting that we have here, it wouldn't be within the candidate list anyways. So yeah, but yeah, thank you for the comment. That's a good comment.
Okay, more questions? So I have a question. So there was a talk this morning by Barbara Plank, looking at annotation disagreement, and I'm wondering, you know, so in your talk you talked about the confidence of the model, but is there a way of connecting some of the things there with uncertainty about the labels, like not for the tasks that you showed as examples, because most of them have, you know, very objective answers, but for those where there might be some disagreements in the label, is there a connection that could be made there?
Yeah, I think so. Sorry, I'm unfortunately wasn't able to participate in the talks because it's very early in the US. But the label uncertainty, I could see how information about label uncertainty and how annotators disagree could be basically directly, you know, incorporated into one of the fine-tuning methods that I talked about here, for example. You know, the exact details of how you would do that would be, you know, what you would have to do research about, but I think it's definitely an interesting question. I've been very fascinated by the idea of like modeling individual annotators since like the paper by like Melody Guan on like modeling different like doctors when they were doing radiology judgments. But I'll need to take a careful look at Barbara's work to have a better idea. So maybe we can talk offline about it.
Okay, so if there are no more questions, I think we can end it here. So, okay, I will pass the floor to Ivan because I think he wants to say something about the breakout sessions, which are going to be the next session. Before that, thanks a lot again, Graham, for